Good morning, sir.
Good morning. So, in the last class, we were discussing about the operational amplifiers, in which some of the positive or open loop amplifier configurations we were discussing. So, that we have seen the crossing detector, zero crossing detector, as a basic comparator circuit. So, comparator is nothing but the basic operation of an operational amplifier is it is going to compare the two input terminals voltage. So which one is greater, correspondingly the output will be get saturated in corresponding saturation voltage. So among the two input terminals, inverting and non-inverting, suppose if non-inverting input voltage is greater than inverting input voltage, so just by 30 microvolts, as I mentioned earlier. So if there is any voltage difference of just 30 microvolt direction is there, so which one is having a larger, so that correspondingly will make them corresponding the output to get saturated in particular direction. So if the inverting input as well as the non-inverting input both are there, so if compared to inverting input, if the non-inverting input voltage is greater, then since we have not employed any feedback, so it is going to the operational amplifier. Basic op-amp circuit is going to work like a comparator circuit. So if it is the non-inverting voltage is greater than inverting, so the output will get in positive saturation. So saturation voltage means 1 volt less than the maximum power supply which you are going to connect over here. So whatever the voltage is there plus VCC, so 1 volt less than the VCC you will get as the output. Whenever the inverting input is will become greater than the non-inverting input, then only the output will switch from the positive to negative saturation. So till that, so the output will be in positive saturation itself. So this is what the comparator circuit is going to do. So same thing, the operational amplifier without any feedback, so it is going to act like a comparator circuit. So now moving into the next, in which we are going to have what we call the zero crossing detector as a sub classification of comparator circuit. So in that in the zero crossing detector circuit, so what we are going to do is whenever the input mm, process the zero, that is the reference voltage, so zero as a reference voltage, so we are going to see whenever the input voltage crosses this zero, so the output we should get detected. So that is nothing but the circuit of zero crossing detector is going to. So for this circuit, so we are going to see the input voltage, so will be given as a will be given to the one of the input terminal, and when another input voltage we are going to give some voltage, so that is a reference voltage. So this is a different application. Okay, so in this in this case what we are going to do is so we are going to take the voltage from the two power supply, and we are going to move across them. We are going to select the reference voltage in particular such a way that so between the positive and negative, since we are, so we are going to move exactly at the center. So whenever it's exactly at the center, so that corresponding terminal, the voltage will be equal to 0. So non-inverting terminal is given with the reference voltage as 0 also. So since the non-inverting terminal will be held at 0, so the another input terminal for which we are going to apply the input voltage. So input voltage is applied to the inverting terminal. So since it is a sinusoidal waveform, so you can see whenever the input voltage is going to cross certain reference voltage level. So here also you can see you can set it to 0 or you can set to certain reference point of voltage, so that whenever the input voltage crosses corresponding reference voltage, then you can see the output will trigger. So until input is less than the V reference, so the output will be in negative saturation, because the output will be in until the input is less than the non-inverting terminal voltage, so that is the reference voltage, then obviously the output will be in positively saturated. So you can see the output is positively saturated until input is less than the reference voltage. So the output will be, because the non-inverting is greater than the inverting input voltage, so non-inverting terminal, since the voltage is more when compared to inverting, so the output is positive, will get saturated in positive direction. So whenever the input is exceeds the value of the reference voltage, just microvolt difference if it is exceeds also. So it will cause the output to switch from positive to negative saturation. So during this interval, so you can see the input signal. So above reference voltage, whenever the input rises just above the reference voltage, and during the positive peak of this, we can observe during this time interval the inverting input will be greater than the non-inverting input terminal. So inverting input that is connected to Vin. So this is always greater than that of non-inverting terminal, which is held at the reference voltage. So during this time interval, so the output will be shifted to negative saturation. So this is what you will be getting, and it will be in this state until the input voltage is greater than reference voltage. So you can see until the input voltage is greater than reference voltage, that is reference voltage. So the output will be saturated in negative direction. And whenever the input goes below the reference voltage during this time interval, the input signal will be moving in the negative of cycle, and it is going to go from this positive voltage less than the reference voltage whenever it appears. So reference voltage will be greater than this one. So the output will be again it will be switched to negative to positively saturated. So this is what switching time, and during this time interval, so the output will be in the positively saturated. So only when it is greater than V reference, it will be negative saturated. Otherwise, the output will be in positive saturated. So the output will be having only two states now. So even if you look at this the waveforms, so you will be having either the output of the op amp will be either positively saturated or it will be negatively saturated. So that is the two cases. You are going to see the output. So no other alternative. So you are not going to get any voltage. So you are going to get either positive saturation or negative saturation. So irrespective of the input signal, okay. So I'm just telling irrespective of the input signal and irrespective of the input signal waveform. So the output will be either in positive saturation or negative saturation, and the output will be in either of the two states. So that is what type of waveform, even if it is a 1 volt peak to peak or 5 volt peak to peak, 10 volt peak to peak, or any type of waveform input. So the output will be either in positive or negative saturation. So this is a circuit for non-inverting type of detector. So comparator. So non-inverting type comparator. So we are going to check what is the voltage. So in order to identify this, what is the reference voltage if I want to identify, because since it is given with this terminals play voltage, so I can go with this circuit. So whenever this circuit you can see, so whenever the input circuit gets roll off, so you can note down that point voltage and you can say that that is the unknown voltage. So you can see what is the voltage of the unknown, what is the voltage of that reference voltage, we can easily note down. So this circuit is an example for non-inverting type of non-inverting type of person detector comparator. And now the same circuit, so if we are going to give the negative reference voltage source, so instead of this positive in this one, so if you are going to apply negative reference voltage, then the output will be called as an inverting type of comparator. So that is what. So whenever the input is goes below or becomes more negative compared to V reference voltage. Oh, wait a minute. I will just come in fraction second. So, sorry, sorry for the inconvenience. HOD sir has heard. Okay, we can see this is nothing but inverting comparator circuit in which we are going to have a V reference as a negative V reference voltage source we have connected to the inverting terminal, and we can see in the inverting terminal, so we are going to connect the voltage source, input voltage source. So for the non-inverting terminal, if I am going to connect a non-inverting terminal, if I am going to connect a negative reference voltage source, so the circuit is going to function as a inverting type of comparator circuit. So as long as the input voltage is since we are going to connect the non-inverting terminal, so as long as the input is connecting to the greater than the V reference, so the circuit is going to be having a negative saturation. Whenever the input voltage we can see, so greater than the V reference is there, so in the negative direction, so the output will get into saturation. Till that term, the output will be in negative saturation itself. So this is about the inverting comparator circuit. So special case of this comparator circuit is zero crossing detector. So in which zero crossing detector, so one of the voltage signals also will be always connected to zero reference voltage. So since we have used in the previous case reference voltage to some particular voltage, so in this case we are going to consider the reverse reference voltage as equal to 0 to the non-inverting terminal. So whenever the input signal exceeds greater than the reference voltage or less than the reference voltage, you can see greater than the reference voltage. So the input, the output will switch from one saturation to another saturation. So during the positive half cycle, whenever the input is exceeds the non-inverting terminal by greater than 0, so during the during the positive half cycle, so you can cause the output to switch to the negative saturation. So this is what you can see. You can see in this whenever the input is greater than 0 volts, so during this, since it is applied to the inverting terminal, so output will be get saturated in negative saturation. And whenever the input exceeds, whenever the input crosses this 0, and whenever it is exceeds the value in the negative direction, so again the inverting input will be greater than compared to the reference 0 voltage. So we will getting the output to be get saturated in positive direction. So this is what positive saturation and negative saturation. So in this circuit, so we can see, so the type of signal input waveform is sinusoidal signal, whereas the output you are going to get as another important thing is so whenever the input crosses the zero line, so zero reference line, so that is from positive negative half cycle or negative half cycle to positive half cycle, you can see during this time interval. So you are also seeing the output to be switching to from one saturation to another saturation. So this is what called the example for a zero crossing detector. So whenever the input signal crosses zero, so here also you can see, so the input crosses from your positive peak to negative peak or negative to positive peak, you can see the output is also going to detect. So detecting in the sense it is going to switch from one saturation to another saturation. So this is an example for zero crossing detector, and in that case, so you're going to see the output input voltage will be being connected, and the purpose of using this clamping diode, so in order to protect the high voltage signals arriving to the input signal, so we are going to clamp the voltage difference of this input stage of amplifier by 0.7 and minus 0.7 respectively. Hence during the positive or negative voltage, so the output is going to clamp to 0.7 and minus 0.7 respectively. So this is an example for zero crossing detector. So today we are going to learn the another application, important application of the operational amplifier is going to employ the positive feedback. So till now, so in the zero crossing detector as well as comparator circuit, so we have not employed any feedback. Okay, so here in the circuit also you can observe. So operational amplifier we are going to use. So pump 741 or 351. So another what type of it is can be BJT type of op amp, or it is an FET type of op amp. So with the open loop amplifier configuration. So we have studied the zero crossing detector, comparator as well as the reference voltage detector. So reference voltage detector. So this is voltage detector we have studied. So now in this today's class we are going to employ the positive feedback. So whenever you employ the positive feedback, so in the oscillator circuits and all, so we have employed the positive feedback. The same way here also, you're going to see the applications of the operation amplifier with respect to positive feedback. So also in the last class, I have just mentioned about the positive feedback as well as open loop. So there is comparison, or there is a certain what is that? So there is correlation between the open loop amplifier as well as positive feedback. So whenever the op amp is acting as an open loop or in the positive feedback, so both will be having the output to be getting saturated in things. So even if you employ the open loop amplifier configuration or the positive feedback amplifier configuration, so you will be getting the output of the op amp will be in positive saturation or negative saturation only. So that is about that is about open loop configuration. So there is open loop as well as there is a similarity between the open loop amplifier configuration as well as the Schmitt trigger application. So, okay, then in this schematic trigger circuit application, if we consider, so the schematic trigger, so it is going to see here the same operational amplifier you are going to see. So op amp. So in this op amp, so we are going to have positive feedback. So till in the previous classes and all, we have an application where we are connecting the output to the inverting terminal, whereas so in the previous in the studied seen the application with respect to inverting configuration. Hello, mute yourself. So in the previous operation amplifier configuration, so we are going to use a negative feedback, but now you can see the output. So kindly mute yourself. Okay, in the previous applications, we are seeing the output was feeding to the inverting input, so that was the negative feedback. So now onwards, for this schematic trigger application, comparator and all, so both are nothing but some of the applications which you are going to learn with respect to positive feedback. So even like on loop operation, open loop configuration as well as a positive feedback configuration, so both are nearly we can call it as the same. Whenever we employ the positive feedback, that is the output connected to the non-inverting terminal, so that is in positive feedback. Uh, output is going to have both will be in the same phase, and in that particular, so we are going to see the schematic trigger application. So in this we are going to study the circuit of this is the circuit of inverting schematic trigger application. Okay, so this is a inverting comparator. So shows an input feedback. So inverting comparator. So the schematic trigger is nothing but not at all different. So it is nothing but the same. Only thing is it is acting like a comparator only. So it's a special case of where we are going to select suitable the reference voltage. So based upon that corresponding reference voltage, it is going to switch the output to switch from one saturation to another saturation, and because of that, so we are going to call it as a comparator, and it is an example for an inverting comparator. So why it is inverting comparator? Because if you are employing any input so to the inverting terminal, so that means the amplifier is going to act like a inverting amplifier, right? So that is another inverting amplifier. But in that, so we are going to have a comparator. So comparator means you should remember. So it is going to compare the voltage that you are going to have as the inverting as well as the inverting terminal. It is going to compare, and based upon that, if the inverting input is greater than the non-inverting terminal, so output will be getting saturated in positive inverting amplifier. So inverting comparator circuit. So input, since it is going to apply to the inverting terminal. So whenever the inverting input is greater than non-inverting terminal, so output will be saturated in negative saturation. So during initial phase, so the output will be saturated in positive only. So when you apply the positive feedback, so you are going to apply the positive feedback. Employ the entire output voltage will be not fed back to the positive terminal, that is a non-inverting terminal. So you are going to apply only the voltage drop. So some part of the output voltage you are going to give it as a feedback to the. Is it clear? So the non-inverting output voltage is nothing but output voltage is up the load resistance RL. At the same time, the output is also going to appear across R1 and R2 resistor as well. So in that, the voltage drop across the output voltage will be having across R2 as well as R1. So complete output voltage will be appearing across R1 and R2. So in that, whatever the voltage of R1 is fed back to the non-inverting terminal. So based upon this, it is going to compare with the inverting terminal. So we know that so output will be either in one of the saturation voltage, right? So when you apply the positive feedback or when you make the operation amplifier to work in open loop configuration, so the output will be in any one of the saturation state. So at the beginning, if you consider as long as the input voltage, as long as the input, suppose input voltage is equal to 0, and the output will be because of the employment of the positive feedback, so the output will be saturated in positive direction, and the output since the output is in positive saturation, so positive saturation means plus or minus 15 volts is there. Then kinds of developed across R1 as well as R2 resistor. So plus 14 volt kilowatt. So if you consider that R1 at 5 kilo, 10 kilo ohm, 10 kilo ohm. So like that, if you across resistor R1 as well as R2, so the output voltage will get divided across these. We are going to choose a different value. So correspondingly, the voltage is also going to have one different. For your application, for your understanding purpose, I will just tell. So the output voltage, so the value of the resistor R1 and R2 is and R2. That means plus 7 volts plus 7 volts will be applied to the non-inverting. Sorry, 7 volts because of the feedback. So you will be having 4 or 5, 7 volts respectively. So 7 volts will be given as feedback. So non-inverting terminal will be greater than the inverting terminal because the input voltage is 0 at present. So output voltage is 14. So plus 7 is given as feedback. So the non-inverting terminal the reference voltage of. So since the 7 voltage is greater than the 0, so the output will be in positive saturation only. So because non-inverting is greater than inverting, so output will get saturated in positive direction itself. So now whenever the input voltage which you are going to connect to the inverting terminal exceeds plus 7 volts by microvolts, okay. So by microvolts difference, if it is greater than 7 volts, then what will happen? So if it is exceeds by plus 7 volts, the inverting terminal will become greater than the non-inverting terminal. So that inverting terminal, if it is greater than the non-inverting terminal, means so obviously since it is a comparator circuit, so I'm just telling it is a basically as a not told as a schematic trigger, it is just like but so and so yes, the negative voltage at the inverting terminal. So it will cause the output to switch into the positive direction. So this is the inverting terminal. So that is going to cause the output to switch from so positive non-inverting going to be in the positive saturation. So whenever inverting whenever the positive So this is the so it will be get saturated in positive direction. So now whenever the input voltage exceeds this the reference voltage of plus 7 volt, it will cause the output to switch from positive to negative saturation. So this is what. So whenever here he is giving example of plus 14. This is a plus trigger voltage as 25 millivolts as well as minus 25 millivolts. So whenever the input exceeds greater than, for our example, if it is greater than plus 7 volts, then it will cause the inverting terminal to be greater than non-inverting. So it will cause the output to switch to the negative saturation. So it will be in the negative saturation as long as the input is greater compared to the this terminal. So now what will happen? Suppose inverting terminal voltage non-inverting ಗಿಂತ ಜಾಸ್ತಿ ಆಯಿತು. So it will cause the output to switch to the negative saturation ಆದಾಗ what will happen? The output will switch to the from positive to negative saturation. So negative means what? Minus 14 ಆಗುತ್ತೆ. So minus 14 when it happens, what is the voltage drop across resistance R1 and R2? So now it is again changed. So minus 7 volts, minus 7 volts. So now the non-inverting terminal is held at minus 7 volts respectively. Okay. So minus 7 volts ಇದ್ದಾಗ, so that is the reference voltage for this now, as of now, because of previous was plus 7 and plus 1 because of positive saturation ಇದ್ದಾಗ. Now whenever inverting input greater exceeds the value of non-inverting terminal, then it will switch the output from positive to negative saturation. So negative saturation causes the output to change. So across resistance R1 and R2, that is, it will become minus 7 and minus 7 respectively. So minus 7 volts it will be giving as a reference now. So now non-inverting terminal is held at minus 7 and this terminal is still in the positive direction. So it is still going to be, you can see during the whenever it increases, will switch to the negative saturation means so the output the input, the inverting terminal input is greater than this non-inverting terminal, and it will be in the negative saturation until the inverting input exceeds the non-inverting terminal in the negative way. So minus 7 ಗಿಂತ ಜಾಸ್ತಿ ಆಗೋವರೆಗೂ, so the output will be in negatively saturated. So you can see the output will be saturated in the negative direction until the input exceeds this minus 7 volts. So whenever it exceeds minus 7 volts, then only the output will switch from negative to positive saturation. And positive saturation ಆದಾಗ again, so you can see the output is going to shift in the positive direction. So plus 14 volts it will be happening. So plus 14 volts ಅಂದ್ರೆ ಮತ್ತೆ the resistance R1 and R2 it will be equal to 7 and 7 volts respectively. 7 ಆಗುತ್ತೆ. So again 7 volts will be taken as a reference. So this minus 7 and plus 7. So that is nothing but a trigger point voltage. So that is called the trigger point voltage. So I am just using the word trigger point. Why? Because so that is the based upon the selection of this resistance R1 and R2. So the voltage across R1 will be considered as a trigger voltage as this one. So why? Because whenever the input reaches this, so it causes the output to switch from positive to negative saturation. So that is what positive to negative saturation. So negative to positive to negative saturation, that is the lower trigger point. So whenever it reaches the lower trigger point, it causes the output to switch from positive to negative saturation. Whenever it reaches the sorry, this is upper trigger point. Okay, so this is upper trigger point. Whenever it reaches the upper trigger point, so the output will switch from positive to negative saturation. And whenever it reaches the lower trigger point, so it will switch the output from negative to positive saturation. So this is about the Schmitt trigger application. So on this they have just taken example for this one circuit. In this circuit, so they have taken example for the given input signal as a peak voltage is 0.5 as well as a negative peak voltage is minus 0.5. That is nothing but so it is going to have 1 volt peak to peak. Which we are going to connect it here is 1 volt peak to peak. So in which it is going to have a positive peak of plus 0.5 and negative peak of minus 0.5 voltage. So whenever the upper trigger point voltage is connected to as 25 millivolts and the lower trigger point VLT VUT. So this is the number upper trigger point as lower trigger point. So this is the number upper trigger point. So in this corresponding, so this is nothing but the upper trigger point. Whenever the input signal exceeds the upper trigger, switch from positive to negative. So this is a inverting schematic trigger, as I am mentioning. So this is upper trigger point. So and this is the lower trigger point. So whenever the input exceeds greater than the upper or lower trigger point, it will cause the output to switch into the saturation voltage. So it is going to switch from positive to negative, and whenever the input signal reaches greater than lower trigger point, it will switch output from negative to positive saturation. So this is how it is going to work for the schematic trigger application. So the value of what is the kind of value we are going to choose for resistors R1 and R2. So that is the design part where you are going to make the trigger voltage. So in the lab also they have given with the three different cases, right? So what is zero hysteresis, positive hysteresis, as well as negative hysteresis. So this and all things might be discussed in the lab. Hello.
Sir, Sunil sir.
Sir.
Which module, sir?
Sir, good afternoon, sir. Sir, module 4, sir. Last legend, sir.
Last
module.
CO4
module, last topic. Last topic.
So ಮತ್ತೆ knowledge level ಏನು ಬರುತ್ತೆ ಸರ್?
So CO4 ಬರುತ್ತೆ ಸರ್, K3 ಸರ್.
ಪ್ರಾಬ್ಲಮ್ ಮಾಡಬೇಕು.
CO ಇವಾಗ ಥಿಯರಿ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ ಸರ್ ನಾನು. ಅಪ್ಲಿಕೇಶನ್.
ಸರಿ, ನೀವು ಕಂಟಿನ್ಯೂ ಮಾಡಿ ಸರ್.
ಥ್ಯಾಂಕ್ ಯು. So in this the value of the resistance R1 and R2, so this selection of this proper selection of this resistance, it is going to cause the upper trigger point as a lower trigger point to vary. So if you have the equal value resistance, then you will be having the upper trigger point as well as lower trigger point both. So in this case here you can see upper trigger point is selected as 25 millivolts, as well as lower trigger point is also minus 25 millivolts. So this indicates what? So in the output waveform also you can see, so you can do the comparison as well. So in this figure itself, so since the upper trigger point as well as lower trigger point are both are same, so only thing is magnitude has been changed because the output is going to have from saturation. So you will be having 25 millivolts as well as minus 25 millivolts. So that is the remote trigger point, and both are remain same. So in this case, so whatever the input signal waveform exceeds just about 25 millivolts or minus 25 millivolts, so you can see the output getting switching from one saturation to another saturation. At the same time, the whenever it reaches or exceeds input voltage exceeds greater than lower trigger point voltage, so it causes the output to switch from negative to positive saturation. So in this case, what you can observe is, so one period of the cycle output waveform you can see, so 50% of it is off and 50% of the time it is on. So for a given one input cycle, so one signal output input waveform, so the output also you can see, so it is going to have 50% duty cycle. So 50% duty cycle is nothing but the percentage of the time the output signal is on. So percentage of the time the output is on is 50%. So that is why you will be getting a perfect square wave as a output. So you can see the time duration off time as well as on time. So you know the duty cycle, right? So duty cycle is nothing but for a given signal waveform, what will be the on time as well as off time. So that is nothing but duty cycle on as well as duty cycle off. So one time period will be having 50% duty cycle on and 50% duty cycle off, it is there. So you can see a perfect square wave as a output will be getting. So this is about the inverting schematic trigger circuit. So now along with this very important thing, so you can see in this hysteresis curve. So in this hysteresis curve also you can analyze the circuit. In this hysteresis circuit, so you can see this is the input and output respectively. This is nothing but transfer characteristic. We can also call it as a transfer characteristic or hysteresis cycle. So wherein which you can have the plot of input voltage versus the output voltage. So you can see along the x-axis you are going to have a positive input voltage as well as here is a negative input voltage, and this is upwards is nothing but positive output voltage, and downwards is nothing but negative output voltage. So you're going to see the hysteresis, that is the operation of this inverting schematic trigger circuit. So now along the x-axis this, as I mentioned, so the input you're going to increase. So during this positive half cycle, you have to consider. So this is a waveform which you're going to give during the positive half cycle, that is V in during the positive half cycle, and during the negative half cycle, you're going to observe the waveform towards the left side. So this is the center origin 0, 0. So now the input signal, whenever the input signal is 0, so when the input signal is 0, since it is a positive feedback, so the output is getting saturated in positive direction. Since the output is connected to the non-inverting terminal, so this is going to have a feedback, and for a positive feedback, you have to remember it will be having only two states output. So one plus VCC and minus VCC, that is the upper VCC V saturation and minus V sat will be getting as output. So whenever you are not applying any input voltage, so or whenever the input voltage is equal to 0, so output will be saturated in the positive direction because of the feedback, positive feedback which you have employed. So you can see the output is in positive saturation. So you can see this is a plus V sat. So as you increase the input voltage, so you can see the output will be in the positive saturation itself. So as long as the input voltage is less than the feedback voltage, or the less than the non-inverting terminal voltage. So non-inverting terminal voltage is nothing but your the voltage drop across R1. So that is nothing but trigger voltage. So as long as the input voltage reaches the trigger point, so this is nothing but a trigger point. As long as the input voltage is less than the upper trigger point voltage, so this is the trigger point voltage. So as long as it is less than the upper trigger point voltage, the output will be saturated in positive only. So the output will be saturated in positive saturation itself. Whenever the input exceeds this upper trigger point, that means whenever the input is greater than this upper trigger point, so that causes the output to switch from positive to negative. So why? Because so negative, that is inverting input, will become greater than the non-inverting terminal. So it causes the output to switch from so positive saturation to negative saturation. So you can see the waveform direction also. So from the 0, it is going to move from this side, and whenever the inverting input is exceeds the value, so it will cause the output to switch from positive to negative saturation. And still, if you increase the input voltage in a positive way only, so you can see this is the positive direction input voltage. That means greater than upper trigger point when you increase still further, so the output will be stayed in the negative saturation itself. Why? Because whenever the output voltage triggers from positive to negative saturation, correspondingly the reference voltage is also going to change, because it will become minus Vsat. So minus Vsat means it will become equal to, the reference voltage is going to switch to minus 7 volts. So minus 7 volts ಆದಾಗ, so since it is a positive voltage is greater than this negative voltage, so it will be up to minus 7 volts. So the output will be in negative saturation. So during this portion of the input, so you can see this is the input. After a trigger point, you can increase and then still reduce, and it will become equal to 0 also. It will be in negative saturation only. So the output will be in negative saturation. As you reduce the value of the input voltage, so the output is also will be stayed in the negative saturation only until it reaches the lower trigger point. So this is the voltage at which the lower trigger point has reached. So because of negative saturation, so lower trigger point voltage is corresponding, for my example, minus 7 volt. So minus 7 volts ಬರೋವರೆಗೂ, so it is going to be the negative saturation only. So output will be in negative saturation only. So whenever the input exceeds greater than this minus 7, that means so the output, whenever the input signal exceeds this lower trigger point, so in terms of minus 7, minus 8, minus 9, like that, if you keep on increasing the input voltage, so this keep on increasing the input voltage, so at that instant, so the output will switch from negative to positive direction, that is positive saturation, and it will be remain in during this entire portion up to it reaches the upper trigger point. So the output will be in saturation, positive saturation, until you reach to the maximum value, or you can go down, and until it reaches the lower trigger point, the output will be in negative, in the positive saturation itself. So this is the curve, and you can see for a given input and output how we are going to get. So hysteresis. So already you might have studied in physics and all, hysteresis curve and all. So the same thing we are going to learn in this schematic trigger topic also. in this schematic trigger project. So the hysteresis wherein which you can see this is the cycle you are going to observe for a given input cycle. So it is going to be keep on continuing this and you will be getting the output or hysteresis curve. So hysteresis is nothing but hysteresis. So what is the value for this hysteresis? So you will be having zero hysteresis, positive hysteresis as well as negative hysteresis. Okay. So if the trigger point, so upper trigger point as well as lower trigger point both are same, then you will be having, so when you take the difference between these two, upper trigger point and lower trigger, so this is the limit of upper trigger point and this is the limit of lower trigger point. So when you take the difference between the upper and lower trigger point voltage, then you will be seeing the what is the hysteresis curve for this schematic trigger. So if you select the suitable resistance R1 and R2 both are equal, then you will be having both upper trigger point as well as lower trigger point value will be same, and hence you will be getting the hysteresis curve as 0. So upper trigger point is what? So it is in this case example upper trigger point is 25 millivolts. So lower trigger point is what? So minus 25. So we will be having hysteresis as 0. So the same thing he has given. So we need to find out what you mean by how we are going to find out the upper trigger point voltage as well as lower trigger point voltage. Okay. So this lower trigger point and upper trigger point design we need to do. So how we are going to do the design? So whenever upper trigger point or lower trigger point, so I am just telling, so lower trigger point or upper trigger point if you consider, so that is nothing but the voltage which is going to be applied across to the non-inverting terminal, so that is nothing but a trigger point voltage. So resistance R1 is going to act as the voltage trigger point voltage for this inverting schematic trigger circuit. So what is the value of the voltage across R1? So how we are going to find? So voltage across VLT or VUT. So VUT is upper trigger point voltage, VLT is a lower trigger point voltage. So VLT or VUT. So we are going to get this upper trigger so voltage with respect to what? So V0 into R1 divided by R1 plus R2. So this is what we'll be getting as the trigger point voltage. Okay, so with this sorry, just wait a minute, wait a minute, I'll just so, if you consider the upper trigger point voltage as well as lower trigger point voltage, so upper trigger point voltage, so as well as lower trigger point voltage, it is going to be the voltage of across R1. So V0 into R1 divided by R1 plus R2 is the voltage in order to find out the upper trigger point as well as lower trigger point. So only thing is that a plus as well as minus you are going to have for positive upper trigger point voltage as well as negative trigger point voltage respectively. The same thing here has been written. So upper trigger point voltage is so you'll be having a positive V saturation. So there is nothing but V0 itself. So V0 is nothing but a positive V saturation into R1 divided by R1 plus R2. So that is the upper trigger point voltage. So in order to find out the upper trigger point voltage, so in that case the output voltage will be in positive saturation. So that you're going to have this as the design circuit for the positive saturation. Same thing, so negative saturation of vector. So output will be in negatively saturated, so the output will be in minus V sat respectively. So design part will be R1 divided by R1 plus R2, so that will be same. That means you can see the voltage drop across R1 is going to act as the upper trigger point voltage as well as lower trigger point voltage. So with this, I'll just conclude today's, and we can also see the hysteresis, that is the upper trigger point voltage minus lower trigger point voltage. So you're going to have this as the example. So R1 divided by R1 plus R2 will be common. So plus V sat minus V sat. So V sat you're going to get. So this is going to be the hysteresis curve in order to find out what type of value it is going to have. Positive hysteresis, negative hysteresis, and all. So in the next class, I will just finish it off this thing. Okay. Okay. With this, I'll just conclude today's class.
Thank you, sir.
Okay.
Thank you.
Thank you.